Bright Duty. Every student matters.
So the first step is enrichment of ore. Gangue is a word which is given for a sand and soil which gets mixed with the ore and makes it impure. So as you can see here, this is an ore of iron and on it is deposited sand all over here and here. So this kind of mix of sand and soil which gets deposited with the rock needs to be removed before we start with the chemical processes. So to remove it, there are different kinds of processes. They can one example is that sometimes we convert the ore into molten forms, and all these impurities are very light. That is why they float on the top, and then they can be removed. So one option is melting the ore. There are different options based on the impurity. So based on the physical and chemical properties of the impurity, we choose the process for refining of this ore. They must be removed before extraction. The process depends upon the properties of the impurity. Electrolyte is the substance which consists of aqueous saturated solution of copper sulfate. This solution is acidylated with sulfuric acid to make a better conductor and prevent hydrolysis of copper sulfate. We create the following setup as seen, and at the cathode we have a strip of rod of pure copper metal. It is connected to the negative terminal of the battery. At the anode, we have an impure cylindrical block of copper. It is connected to the positive terminal of the battery. The electrolytic dissociation is the process. So before the passage of the current, following ions are present in the electrolyte. Inside there is, from the copper sulfate solutions, there is Cu plus and SO4 2 minus. From the sulfuric acid there is H plus and SO4 2 minus. From the water there is H plus and OH minus. These ions are present in the solution, which is acting as the electrolyte here. So once we see that all of these are present in the electrolyte solution, we understand what is going to happen. So what happens when we pass the current is that at the cathode, Cu plus and H plus are being positively charged, migrate towards the cathode. However, only Cu2 plus ions discharge the preference to H plus ions because the position of Cu plus ions is lower in the metal activity series. This is happening at the cathode, as you can see in the video. Cu2 plus 2 electrons forms Cu, which is pure copper metal, starts getting deposited at the cathode. The copper atoms so formed deposit themselves on the strip of pure copper. Now at the anode, OH minus ions migrate to the anode but do not discharge. It is because the copper atoms in the impure copper anode have lower reduction potential than the OH minus ions. Thus, copper atoms discharge to form copper ions and enter the electrolyte. So, they are entering the electrolyte from the anode and they are getting deposited at the cathode. So, Cu minus 2 electrons form Cu2 plus, which as we seen in the previous reaction deposits at the cathode. The impurities present in the anode can be of two kinds. The impurities of metals whose position is lower than the copper in the metal activity series, such as silver or gold. This is one kind. The other kind is of those metals which are higher than the copper in the metal activity series, such as zinc, lead or iron. These impurities can also be present at the anode. The impurity mentioned in the first part just dropped down at the anode. It is commonly called as anode mud. Anode mud is not a waste product and it is refined to obtain pure silver and gold. So it is also not getting wasted in this process. The impurities which have higher order metals ionize and enter in the electrolyte. However, they do not discharge at the cathode as long as copper ions are present in the electrolyte. So in conclusion, the atoms of pure copper continuously get deposited at the cathode due to discharge of Cu2 plus ions. Thus, the weight of cathode containing pure copper goes on increasing. And as we continue to pass the current, the copper atoms at the anode continuously ionize to form Cu plus ions at the anode. Thus, the weight of anode goes on decreasing. The impurities present in the copper either deposit in the form of anode mud or dissolve in the electrolyte. However, impurities do not discharge at the cathode. So, we have obtained pure copper metal at the cathode here, and it is getting and the impurities are getting removed in the form of electrolyte or in the form of anode mud. Okay, so once we have received a gangway free ore, then we go on to the process of true extraction. Now first we will be discussing the low reactivity metals. So low reactivity metals like mercury, copper, they exist in form of sulfides. So more often they exist in form of sulfides, and they can simply be reduced by heating. So what is reduction? We'll go on further. But for example, let's take cinnabar, which is the name of the ore of mercury. So different ores have their own common names. So we take cinnabar, we add oxygen to it, like we heat it in the presence of oxygen. This heat has to be there. It results in the formation of oxide. Now the oxide that we have obtained here, we again heat it. Heat and triangle is just a symbol of heat, so you can also use this, or you can just write heat. And then you get pure metal, right, like this. So the process is, the first step is heating. By heating, you will be able to change the sulfide to oxide because of the air present in the air, because of the oxygen present in the air. And the second process is reduction. So reduction is, why is this reduction? As you've studied before, reduction is removal of oxygen or addition of hydrogen. So we are removing this oxygen from the metal, and that is why it is a reduction process. The reduction simply requires heat, nothing else, because they are very low reactivity elements. They break apart easily. Similar process will go for Cu2s, which is again an ore of copper, and when we heat it simply in the presence of air, we can reduce it to pure metal form of COA, right? So for the metals of low reactivity, to extract them, they are often present in form of sulfide. So the extraction process starts with heating them in the presence of air, which will result in the formation of an oxide. The oxide can then be reduced by simply just heating the oxide. Now going on to the middle reactivity series, we have iron, zinc, lead, copper, etc. here. These elements are present either as sulfides or as carbonates. There are two of the major possibilities, that they either combine with sulfur or with carbonate ions. So because it is very hard to extract the metal directly from sulfide or from carbonate, we first convert them into oxide. Either way. So first attempt is to convert them into oxide, because from oxide they can be reduced by two very common methods that we'll discuss later on. And the process for converting them into oxide are called as roasting and calcination. So for sulfide, we use roasting, and for carbonates, we use calcination. So what happens is that for the conversion of sulfide ores into oxides, the process is called as roasting. The process is very simple. We just heat it in presence of a lot of air. There should be enough amount of oxygen present in the situation when we are heating it. The sulfide will react with the oxygen, and on heating it will form oxide, and the sulfur will get oxidized, right? Similarly for carbonates, the process is called as calcination. So if you want to remember, you can just create it in your mind that carbonates go with calcination, and then roasting goes with sulfide. So for carbonates, lesser amount of air is required because the reaction does not involve oxygen, it just requires heat. So it is heating with limited amount of air present. You heat ZnCO3, it forms ZnO and CO2. So again, zinc was present in two forms of sulfur, as a sulfide and as a carbonate. Here for sulfide, we use enough amount of oxygen and then we heat it to form an oxide. Here we use just heat, and because oxygen is not part of this equation, there is limited air supply here, and it results again in the formation of ZnO. once we have obtained oxide, either by calcination or by roasting, then it is very easy to reduce it. There are two main methods of reducing it. One is reducing with carbon in coke form. Coke is just a way in which carbon exists in nature. And then another is displacement. First, let's discuss carbon. So we add this zinc oxide to carbon, and it reduces the zinc oxide and forms CO gas. So this oxygen is taken away by the carbon and zinc is obtained in pure form. This is a process of reduction. Right? It's a redox reaction. Sometimes it so happens that these elements, it is not possible for us to use carbon because they have so high affinity for oxygen that this process will not happen in this way. So in that case, we use this different approach. We use highly reactive metals like sodium, calcium and potassium. So we had studied previously that highly reactive elements replace the metals of lower reactivity from their solutions or from their compounds. So in this case, when we use these elements, they replace the metal from its oxide and lead to the formation of pure metal and the oxide of these elements. One example here is of manganese. So we have manganese oxide. We reacted with aluminium, we get pure manganese and aluminium and a lot of heat. So this reaction is highly exothermic. In fact, this reaction is called as thermit reaction. In this reaction, it is so exothermic that it can also be used to join the railway tracks. We'll study this further when we are answering certain questions. But you can understand right now here is the thermit reaction is a highly exothermic reaction. When we use a different metal, a metal of much higher reactivity, to extract from its ore, from its oxide, the pure metal. So we are using, for example, in manganese here, we are using aluminium, which is highly reactive, to extract manganese from its oxide. This reaction would be thermit, and it is called thermit because of therm means heat. So it releases a lot of heat. This reaction with iron is also used to join railway tracks. So that is about that for mildly reactive elements, we have first two processes, calcination and roasting. Calcination for carbonates, roasting for sulfides. Calcination is done with limited air supply and roasting is done with high air supply. From both the processes, we finally receive oxide of an element. The oxide can then be reduced by two ways. First, by reduction by carbon in form of coke, and the other is a displacement reaction by a highly reactive metal, one of which is thermit reaction. Okay, so now that we have understood how low reactivity metals and medium reactivity metals are extracted, let's move on to the highly reactive metals. Now these metals cannot be reduced with carbon because they have a higher affinity for oxygen. Simple as that. They are so strongly bonded with oxygen that carbon cannot replace them from the compound. So because of that, we have to use electrolysis. So electrolysis means breaking of something in the presence of electricity. We convert the ore into molten form, and we use the molten chloride form. This is one example given here, that when we convert the ore into a molten form, in liquid form, then at the cathode the metal gets deposited and at the anode the gas of chlorine is released. So the metal, which is in pure form, gets deposited here. So there's no other way, there's no chemical way with which we could react these elements because they are themselves so highly reactive that it will not be possible for anything to replace them from their compounds, and that is why we use electrolysis. We use the electricity to break them apart, and then the metal is released at the cathode and the extra gas is released at the anode. This process is called as electrolytic reduction. So they are getting reduced, they are getting reduced by the presence of electricity. So now let's move on to the final step. Now we have all the three processes for highly, medium or for low reactivity metals. Now once we have obtained them in the pure form, the process does not end there, because even after reduction and even after after heating them, like for the low reactivity metals, what we obtain is still not pure. So it is not 100% or it's not pure metal. Now we need to refine it further. We need to clean it to get all the impurities out of the way. How do we do that? We do this by the process of electrolytic refining. So let's see the setup here. We have a tank. We have acidified solution of the same metal. So if I'm doing this for copper, the electrolyte will have copper in it. If I'm doing this for magnesium, the electrolyte will be a salt of magnesium. At the anode, we use the impure metal. So anode is impure wala metal, the one that we have just retrieved from purification. And at the cathode, we are using a pre-existing pure form, right? Now what we do is, when we connect the circuit and we let electricity pass through it, what happens is that some amount goes from the anode to the solution. So this goes from the anode into the solution. From the solution, an equal amount deposits itself at the cathode. So it's getting deposited on the cathode and becoming thicker. In this process, when this was happening, when it was going from the anode to the electrolyte, the dust was released and it started settling at the bottom. This is called as anode mud. So the impurities that were present, which got broken apart when the anode was dissolving in the electrolyte, get deposited at the bottom when they are insoluble. If they are soluble, then they will get dissolved in the electrolyte. In either case, we have removed the soluble impurities and the insoluble impurities. Insoluble impurities get deposited as anode mud, and the soluble impurities are present in the electrolyte. But the pure metal gets deposited on the cathode, and then we can retrieve it from there. So this process is called as electrolytic refining of the metal. For this, we have three basic steps. Use the impure metal at the anode, use the pure metal at the cathode, and the metal salt as the electrolyte. Then this process will happen where the anode will send the metal into the electrolyte. From the electrolyte, the metal will go on and deposit on the cathode. The same amount of would go on deposit on the cathode, and then we will have pure metal at our hands. So this is the entire process of extraction. The first step was removing the gangway. The second step was different for low reactivity, mild reactivity and high reactivity of metals. The process depended on their chemical properties. The third step was refining of the ore, where we used electrolytic refining to get pure metal. So now this completes the entire process of extraction of metals from their sources. The questions that you might be asked could be of a certain step, or it could be a whole cycle that you can explain with the flowchart explained in the initial